Hi, I'm Bob. Welcome back to the tutorial on how to solve the exercises for the textbook Microeconomics Theory and Applications with Calculus, the 5th edition. We will answer the questions related to the sequential dynamic games at the end of chapter 13 of game theory. Here's exercise 3.1. Two firms are planning to sell 10 or 20 units of their goods and face the following profit matrix. In part A, what is the Nash equilibrium if both firms make their decisions simultaneously? If it is a simultaneous move static game, we write the payoff matrix and use the best response approach to find the pure strategy Nash equilibrium. We first find firm 1's best response. Given that firm 2 chooses 10, firm 1 gets 30 if it chooses 10, but 60 if it chooses 20. Firm 1's best response is to choose 20. We underline the profit 60. Given that firm 2 chooses 20, firm 1's best response is to choose 10 because it brings a higher profit. We underline the payoff 50. Next, we find firm 2's best response to firm 1's actions. Given that firm 1 chooses 10, firm 2's best response is to choose 20. Given that firm 1 chooses 20, firm 2's best response is to choose 10. We underline the corresponding payoffs. We find two cells with both payoffs underlined. They are the outcome of the Nash equilibrium. The two pure strategy Nash equilibria are firm 1 sells 10 units, firm 2 sells 20 units, and firm 1 sells 20 units and firm 2 sells 10 units. We can also find a mixed strategy Nash equilibrium for this static game. Suppose firm 1 chooses 10 with a probability of alpha. We calculate firm 2's expected profits for each of its strategies. If firm 2 chooses 10, its expected profit is 40 minus 10 times alpha. If firm 2 chooses 20, its expected profit is 20 plus 15 times alpha. Firm 2 should be indifferent between its two strategies. We can obtain alpha, the probability at which firm 1 chooses 10, which is 0.8. The same reasoning gives beta, the probability at which firm 2 chooses 10, which is 0.5. The mixed strategy Nash equilibrium is that firm 1 chooses 10 units with a probability of 0.8, and firm 2 chooses 10 units with a probability of 0.5. In part B, draw the game tree if firm 1 can decide first. What is the outcome? Why? It is a sequential dynamic game. We use the backward induction approach to find the subgame perfect Nash equilibrium. The game tree is as follows. There were two stages in this sequential dynamic game. We first consider firm 2's strategy in the second stage. Given that firm 1 chooses 10, firm 2 gets 30 if it chooses 10, but 35 if it chooses 20. Firm 2's best response is to choose 20. We underline its payoff 35 and add an arrow on the path. Given that firm 1 chooses 20, firm 2's best response is to choose 10 because it brings a higher profit. We underline the profit 40 and add an arrow on the paths. Next, we figure out Firm 1's decision in the first stage, given its rivals' responses. If Firm 1 chooses 10 and Firm 2 chooses 20, it earns 50. If Firm 1 chooses 20 and Firm 2 chooses 10, it earns 60. Thus, Firm 1 chooses 20. We underline its payoff 60 and add an arrow on the path. The path with two arrows is the equilibrium path. The subgame perfect Nash equilibrium is that Firm 1 chooses 20 and Firm 2 chooses 20 after 10, but 10 after 20. A strategy is a plan for different situations, so we write Firm 2's strategy as above. The equilibrium path is the path with two arrows. Firm 1 first chooses 20, and then Firm 2 chooses 10. The outcome of the sequential dynamic game is that Firm 1 gets 60 and Firm 2 gets 40. In Part C, draw the game tree if Firm 2 can decide first. What is the outcome? Why? We use the same reasoning as in Part 2. We draw the game tree and use the backward induction approach to find the subgame perfect Nash equilibrium. There were two stages in the sequential dynamic game. We first consider Firm 1's strategy in the second stage. Given that Firm 2 chooses 10, Firm 1 gets 30 if it chooses 10, but 60 if it chooses 20. Firm 1's best response is to choose 20. We underline its payoff 60 and add an arrow on the path. Given that Firm 2 chooses 20, Firm 1's best response is to choose 10 because it brings a higher profit. We underline the profit 50 and add an arrow on the path. Next, we figure out Firm 2's decision in the first stage, given its rivals' responses. If Firm 2 chooses 10 and Firm 1 chooses 20, Firm 2 earns 40. If Firm 2 chooses 20 and Firm 1 chooses 10, Firm 2 earns 35. Thus, Firm 2 chooses 10. We underline its payoff 40 and add an arrow on the path. The path with two arrows is the equilibrium path. The subgame perfect Nash equilibrium is that Firm 2 chooses 10, and Firm 1 chooses 20 after 10 and 10 after 20. The equilibrium path is that Firm 2 first chooses 10, and then Firm 1 chooses 20. The outcome of the sequential dynamic game is that Firm 2 gets 40 and Firm 1 gets 60. Let's solve exercise 3.2. How does your analysis change if the government imposes a lump sum tax of 40 on each firm? That is, the payoffs in the matrix will all reduced by 40. Explain how your analysis will change if the firms have an additional option of shutting down and avoiding the lump sum tax rather than produce 10 or 20 units and paying the tax. In Part A, the firms have three options: to shut down, to produce 10, and to produce 20. We first write the payoff matrix. The profits are all reduced by 40 if they produce. We use the best response approach to find the pure strategy, Nash equilibrium, for this simultaneous move static game. The two pure strategy Nash equilibria are Firm 1 chooses 20, Firm 2 shut down, and Firm 1 chooses 20 and Firm 2 chooses 10. In part B, we draw the game tree based on the payoffs in part A and use the backward induction approach to find the subgame perfect Nash equilibrium. The two equilibrium paths will be firm 1 first chooses 20, and then firm 2 chooses shutdown, and firm 1 first chooses 20, and then firm 2 chooses 10. The outcome of the game is that firm 1 gets 30 or 20, and firm 2 gets 0. In part C, firm 2 moves first. The game tree is as follows. The backward induction also leads to the two equilibrium paths. Let's answer exercise 3.3. Suppose that exercise 1.8 was modified so that GM has no subsidy, but does have a head start over Toyota and can move first. What is the Nash equilibrium? Explain. Since GM moves first, it is a sequential dynamic game. We draw the game tree and use the backward induction approach to find the subgame perfect Nash equilibrium. There are two stages in the game. We first consider Toyota's strategy in the second stage. Given that GM enters the market, Toyota gets 10 if it also enters the market, but 0 if not. Toyota's best response is to enter the market. We underline its profit 10 and add an arrow on the path. Given that GM chooses not to enter the market, Toyota's best response is to enter the market because it gives a higher profit. We underline its profit 250 and add an arrow on the path. We find that Toyota's strategy is that it enters the market no matter what GM chooses. Next, we figure out GM's decision in the first stage, given its rivals' responses. If GM chooses to enter the market, it knows Toyota will also enter the market. GM's profit is minus 40. If GM chooses not to enter the market, it knows Toyota will enter the market. GM's profit is 0. Thus, GM will stay out of the market. We underline its profit 0 and add an arrow on the path. The subgame perfect Nash equilibrium is that GM chooses not to enter the market, and Toyota enters the market regardless of GM's decision. Remember that strategy is a plan for different situations, so Toyota's strategy is as above. The equilibrium path is the path with two arrows. GM first chooses not to enter the market, and then Toyota enters the market. The outcome of the game is that GM gets 0 and Toyota gets 250. Let's go to exercise 3.4. A small tourist town has two Italian restaurants. Normally, both restaurants prosper with no advertising. One restaurant could take some customers from the other by running radio advertising. The profit matrix looks like this. In part A, what is the Nash equilibrium in the static game? We write the payoff matrix and use the best response approach to find the Nash equilibrium. We first find player 1's best response. Given that player 2 chooses not to advertise, player 1 gets 3 if it does not advertise either, but it gets 4 if it advertises. Player 1's best response is to advertise. we underlie its profit 4. Given that player 2 chooses to advertise, player 1's best response is to advertise because it brings a higher profit. We underlie its profit 1. Next, we figure out player 2's best response to its rival's actions. Given that player 1 does not advertise, player 2's best response is to advertise. Given that player 1 advertises, player 2's best response is to advertise too. We underlie the corresponding profits. We find a cell with both profits underlined. It is the outcome of the Nash equilibrium. The Nash equilibrium is that both restaurants advertise. Each player gets 1. It is a prisoner's dilemma game because each would get a high profit if they could cooperate. In Part B, describe one or more possible Nash equilibria if the game is repeated indefinitely. If the game is repeated indefinitely, the player can use the trigger strategy to maximize their joint profits. For example, a player uses the trigger strategy that it does not advertise unless its rival advertises. In that case, it will also advertise from the next period. For its rival, its expected profit if it does not advertise forever is pi Rn. It is an infinite geometric series. Using the formula, we can simplify it as 3 over R, where R is the depreciation rate that reflects the player's patience. If the rival cheats, its expected profit is as follows. The first term is the profit if it cheats, that is, to advertise. It is 4, higher than 3, the profit if they cooperate. The following terms are the profits it gets after cheating. Each is 1, lower than the profit if they cooperate. For the trigger strategy to be successful, that is, both players do not advertise, the expected profit from cooperation should be higher than the expected profit from cheating. We can obtain the depreciation rate R smaller than 0.5. If the player's depreciation rate is low enough, or equivalently, the players are patient enough or care about the future profits, then the Nash equilibrium is that both players do not advertise. Both get 3 in each period. Another possible outcome happens when the depreciation rate is higher than 0.5. The players end up in the single period static game Nash equilibrium. Both advertise and get 1 in each period. In Part C, are there multiple equilibria if the game repeats indefinitely? According to the above analysis, there were 2 possible Nash equilibria if the game repeats indefinitely. If the players are patient enough or care about future profits with a depreciation rate lower than 0.5, then both do not advertise. If they are not patient enough, then both players advertise. Thank you for watching this video and subscribing to my YouTube channel. See you next time.